We're going to be talking about something that's really kind of important. It overlaps into physics and mathematics, but it overlaps in a way that's not going to be particularly offensive to anybody. You don't really need to have physics before you take this class, although by now most of you should already have physics under your belt. But we have to talk a little bit about some physical stuff here, as we will in a second. And before we do that, let's just recap what we did the last time we were in lecture. We didn't do anything in lecture last Thursday because we were at Municipal Park. But when we met on Tuesday, I gave you a lecture talking about basic grain size, parameters, etc. Now, a reminder again, starting Thursday, I'm not going to be doing this review. I'm going to pull somebody from the class and ask you to review these slides. What I will do is just allow you to either come up here if you want to talk about it, or you can talk from your desk, and I'll just go through the slides. When you're ready, just click on to the next one. Last Tuesday, we discussed basic sediment grain size. We talked about ternary plots, including grain size classification. We interpreted some grain size data. We didn't really do any interpretation, but I gave you a couple examples of things and got you to start thinking a little bit about what those data actually mean. And then we talked about grain size parameters. As far as recap goes, this was our introductory grain size slide that more or less talked about how sediment is distributed, how sediment is classified. The main thing to note is that we recognize four major divisions. Gravel, anything greater than 2 millimeters in size. Sand, which is the important one, which is the visible range, goes from 0.063 millimeters to 2 millimeters. Silt and clay. I also talked to you a little bit about what the Phi scale is all about, what that means in general. Then we introduced the whole concept of classification, and the problem that I tried to explain to you was that when you're dealing with sediments and you've got four major divisions, sand, silt, clay, and gravel, it's not really possible to visually put all of those onto one classification scheme. So you really have to choose three of them. And if you choose three, you can do it by the ternary plots that you see here. And ternary plots are really, really, really pervasive in geology because we deal with a lot of different variables. I gave you a bunch of different schemes. This is the one by Folk. It was done in 1954, dealing with sand, silt, and clay. And the way it works is it's empirical. You figure out what the percentages of those three ingredients are in each of your samples, and it will plot somewhere on this chart. I showed you how to do that. And if it plots here in the SM range, then it would be classified as a sandy mud. I also showed you a competing scheme. Actually, I'm not sure if the term is competing is correct or not. It's an alternative scheme, and this is the one I actually prefer. This is by Shepard, published the same year. The orientation is somewhat different, with clay being at the top instead of in the bottom. But again, there are fields that the data is going to plot in, and you would name your sediment after wherever it plots on this. And I also showed you the scheme that could be used for gravels. Down here, we don't use this very often because, frankly, we don't have a lot of gravel in our sediment. Some of you did get gravel. I know that some people have put the Jennifer Squared put a core down and got some really big, I mean, they were pretty large pieces of stuff which is interesting because it was kind of not quite in the middle of the lake, but it was certainly in a channel that was a long way from shore, and you got to ask yourself, where did stuff come from? Well, that's your problem, right? I introduced also the descriptive parameters, and like everything in when you're dealing with data, if you have enough of it, you can actually mathematically model things, and we use standard statistical means by which to do this. Now, this really works if you're dealing with grain size that is done through a different method than I'm going to explain to you today. The method that we're using in the lab doesn't produce an awful lot of these type of data, which means you don't have to do a lot of calculations like this. It's a little bit more physical based. I'll explain the reasons for why we do that when we get to the section as well. Okay, so those were the mathematical ways of doing things. And we talked about other properties too, things like roundness and angularity and size and shape. These are all parameters that are important for you to identify in the field. When you get into the field, you can do an awful lot of this just by hand lens. Although in the lab you can also do it too. When you start processing your samples, you're going to be able to look at the different proportions of sediment, including the sand size component. Well, heck, you might want to just look at it under a microscope. Aaron, you wanted to consider rounding and stuff, right? Well, you might be able to get additional data just by taking the sand after you do the grain size analysis, looking at it under the binocular microscope that's in the lab, and seeing if all the grains are well rounded or angular or what. Okay, so you can do additional stuff if you wish to. just remember that most of your data that you're going to be getting from here will be derived from the grain size analysis. All right, so that's what we did last Tuesday, and of course Thursday we were in the park, and it was a nice day for a walk in the park. Today what we're going to be doing is a pretty adventurous day. We're going to be talking about how sediment basically moves. And this is where the physics comes into it. And I'm not going to go into a lot of math over this, so we do have to talk a little bit about some important mathematical relationships. But what is so often nice in science is that you can actually start making assumptions. And while those assumptions are not always good assumptions, if you're consistent, you can actually use cut down versions of this math to do pretty good analyses like grain size. Today we're going to introduce how sediment moves, talking about 6 different modes of sediment movement. We're going to talk about fluid dynamics, and this is under ideal conditions. This is what a physics class would be talking about in terms of how things flow. And indeed, a lot of the stuff we understand about sediment movement was first done by looking how water moves through a pipe back in the 1600s. We're going to talk about how sediment moves initially. There's actually a lot of complications getting a grain of sand to move from one point to another. It does want to go. There's a certain amount of inertia, so you need to overcome that inertia. We're going to talk about some nasty mathematical relationships. They're not things you have to worry about in terms of math, but they are used to determine empirical fields where sediment can be determined as whether it's going to move or not. You're going to love this one. It's totally useless in my humble opinion. But there are some more useful ones. Eulstrom's diagram is a classic example of that. So we have a lot of things we're going to be talking about, but you don't have to worry too much about this in terms of applying it for what you're doing today. Let's talk about sediment motion, shall we? I brought in a baseball because I needed to give you an idea of just what sediment is like. Now assume this is a quartz grain sitting along the bottom of a stream. The current is moving from here in this direction. This is a round particle that can be influenced by currents, and it can be influenced to move under a couple different conditions. All right. So first of all, unless the currents are moving fast enough, nothing's going to happen to this. The grain is stuck there. Now, while that may not seem like a mode of movement, it is one of the states of movement. Non-movement is a state of movement in the grand scheme of things. But if the current is sufficient and it's moving this way, a round grain can be moved by simply rolling along the bed of the stream. Now, I'm using a river or a stream as an analogy how this could move, but there's no reason why a grain sitting in a parking lot quietly doing nothing might be moved when the wind blows, because wind under this definition is also a fluid. Okay? If the grain isn't exactly round, mica flake for example, it's not going to roll, but it could slide along the bottom. In fact, a grain like this can also slide along the bottom if it's not round. Or it could literally intermittently bounce along the bottom. Now that bouncing motion ultimately is called saltation. That's the proper term. It's very common, especially with round grains. They literally would just occasionally jump in the water like this and move down current, always in the direction of the current. Now those 3 that I told you, rolling, sliding, and saltation, all involve the grain in physical contact with the substrate. All 3 of these modes of movement are said to be traction. When you're talking about traction in placement or traction movement, that means the grains are in contact with the substrate. Maybe not always. The bouncing motion of saltation, that's only intermittent contact, but it still is contact nonetheless. It is possible, if you have a grain that is small enough and the current is great enough, or if the current is really quick, to have that grain more or less get into the water column and more or less stay in the water column. It might touch down periodically, but for the most part, spending most of its time in suspension. So suspension is yet another means by which you can have grain movement. Now let's add to this list rest. And in fact, let me just switch to the other slide here so you can see all these. Resting where there's no motion, rolling, sliding, saltation, suspension. Those are the modes of movement that we normally think of when there's a current either water or wind. But there's another one I want you to be aware of. And I want you to be aware of it now, because until we start talking about alluvial fans, and this is quite a few lectures in the future, we're not going to come back to deal with this. It's mass flow or viscous flow. Viscous flow involves not a current, but the movement of a mass, primarily because of gravity. Consider the following. You've got a hill with a pile of loose stuff up here. Suppose someone takes a wheelbarrow up to the top of the hill and dumps wet concrete. That concrete will start to ooze down the slope. Ultimately, it's the force of gravity that is operating downwards that is causing this to move down. But it is related also to the water content. The wetter the substance, the more oozability it's got. Oozability, is that a word? I make up so many words. All of that is referred to as viscous flow. Now you can model viscous flow through a diagram like this, which measures the different pourability or flowability at different levels within a pipe. Remember I told you how a lot of this stuff is modeled on how pipe flow works? This is looking at the viscosity of water. And what it's showing you is how much displacement takes place at each level in a pipe over a certain current. As I said, viscosity and these properties are all physically measurable things, but in this program, in geology, we don't largely measure viscosity by putting a number on it. We look at it in terms of what the end product is going to be. So, and again, this is kind of jumping ahead now, and it's really off topic given what we're talking about, but I'm not going to have another chance to talk about this until we get to alluvial fans. And I want you to be aware of motion, either current in place or through viscous flow. These are different types of viscous flow that are related to the amount of sediment to water in suspension. At this end, we have the most dense material, or if you wish, it has the highest amount of sediment to water content. On this end, we have more water than sediment. Now, we haven't talked about this in terms of this course yet, but most of you have already dealt with this aspect of viscous flow before. If you ever had an instructor, probably in Geology 111, talk about turbidites or density currents, does that ring a bell? The idea at the edge of the shelf, if you have a landslide, what happens is you get water mixed in and you end up having this current that is hugging the bottom because it's being driven by the density of the mass of sediment and water in it. That is because the turbulence of the water is keeping the particles suspended, and down it comes. Those density flows, incidentally, can go a long way. There's evidence that density flows go over thousands of square kilometers, because once they start flowing, nothing's going to stop them until the energy of the movement dies. At the other end, well, again, think back to your wet cement. If you dump a pile of wet cement on the top of a hill, how far does the cement get before it stops flowing? Once the water kind of is lost, it ends up turning into a mass, and you'll end up having a mass of stuff. And indeed, we see this very type of deposit at the top of alluvial fans. And between these two, we actually have different ratios of sediment to water. We're going to get different deposits. Every one of these things gives rise to a specific type of depositional product, from turbidites to these mass flow deposits to everything in between. And when we get to the alluvial fans, I'll talk more about them, okay? But this is the last chance we're going to have to talk about these things as a means by which to move sediment from point A to point B, because I really want to talk more about how the currents work. Now, we're going to talk a little bit about so-called real fluid flow, and you're all aware of what real is, like ideal flow. It's when you take out all the variables. This is what should happen. But this is one of the things that gives rise to the whole concept of chaos theory. Have you heard of chaos theory before? It was very popular about 15 years ago, and now people forgot all about it. Chaos theory was basically somebody coming along the line saying, like, things are so complex we'll never model it. There's just too many variables. In fact, in some cases, that is what applies to flow in currents like we have in geology. But let me try to illustrate how erasers? Oh, there you go. How this works in terms of our topic for today, the idea of movement of sediment. Imagine now that you have got a cross-section through an aquarium or a river or whatever. This is a standard diagram we use. A current will be moving in this direction at a velocity of u. All right, so water is moving ideally in this direction. Now, ideally means that the whole body is moving en masse, although that is literally dependent upon how fast the water is moving. We can model water movement by envisioning what would happen if we were at a starting point, call this t equals 0, and how far the water particles, the molecules, or if you wish, little bits of dust or ink in the water, would travel after a given time. So if this is t equals 1, a particle here can move to that point. The one down here would move there, one here would move there, one here would move there. But you see, once you get towards the bottom, you now start having interactions with the substrate itself. There's a certain amount of frictional contact. The current literally slows as you get towards the bottom. And right here, right at the very bottom, there's no motion whatsoever. This gives rise to a standard flow line diagram that looks like this. How far water will travel in a given point, it decreases as you get towards the bottom. Now, realistically, this is greatly exaggerated. It's exaggerated to show you more or less the shape that you get, that the velocity drops as you get towards the substrate. In reality, if you were looking at water, it probably would do this. Because really, it's only the stuff that's on the very bottom that is going to be slowed down. Any way you want to look at it, if the water is moving like this, it's moving in laminar fashion. And this is called laminar flow. If you've ever seen some of the commercials they have for modeling, usually it's Mercedes-Benz or Beamers that will have this advertisement where they'll show this beautiful black car in a wind tunnel, and they have this gas emitted in the wind tunnel, and you see the streams coming off from it. That's actually laminar airflow. And the idea is that you can watch how the air comes over the body of the car, comes to the other side, and as long as there's no disruption in the air coming off the back, it is ideally traveling as a the body is in such a shape that the air will pass over it in laminar fashion. No turbulence means you don't get slowed down. Not quite frictionless, but pretty darn close, all right? As close as we can get in reality. Now, that's laminar flow. Not all flow is laminar. This diagram is showing you here what turbulent flow would look like, at least according to these guys. Turbulent flow means that from starting point 0, the flow lines don't necessarily move like so. They cross each other. And indeed, there's no reason why you should have them actually going the same point. That particle might only end up there, that particle here, this particle might in some cases go back the opposite direction. Turbulent flow is when stuff is going all over the place. All right, so that's my version of turbulent flow. Both of these are important in geology for moving sediment or keeping it moving. In fact, both of these are important for a lot of things, including keeping airplanes in the sky. All of this stuff, as I said, was first done when modeling how fluid flows through a pipe. And basically what the pipes did was it gave you a confined flow. Now, wasn't around when this was being done in the 1600s, obviously, but the results are very well known. And it's well known, for example, that at a certain velocity, the water will remain laminar. But as you increase the velocity, then you'll start seeing motion going turbulent. And what you'll see is, in this case, this is water passing through a tube, and ink bleb is distributed here. All of a sudden, it will break up into its own pieces because you go from being laminar to turbulent. What controls that, however, is really, really hard to understand. That's why physicists turn to the idea of ideal flow. Realistically, you can have a situation that looks like this, repeat the circumstances exactly, and it goes turbulent. So there's some variables in here that are so finicky that it can change from one thing to another. which is why a lot of people start thinking like, well, maybe it's chaos theory, right? There's some difficulty in doing all this, okay? Pipes are not very good things for modeling the real world, because in the real world, as geologists, substrates are never flat and perfectly smooth like this. There will be bits where there are grains sticking up, there are boulders sticking up, and a flow line coming here is deflected up in that direction, and what does that do to the other flow lines? Ultimately, it draws them into being turbulent. So when you look at a river, stretches that are laminar flowing versus those that are turbulent flowing can change periodically. As the velocity of the water changes, it will change. As the volume changes, so it goes from one thing to another. So I don't spend a lot of time talking about turbulent versus laminar flow here because it's so fickle in terms of what controls it. Far more important to see the applications as to why it's important. It's important in terms of setting up things like eddies and showing you how deposition ultimately is going to work. What you're looking at here are a couple situations that will show you how things ultimately are going to occur. This is a current with a very sharp bend on it. You're looking at planar view here. Laminar up here, comes across like so, isolates this little body. Next thing you know, you have a current that is stuck here. That it's probably better showing you here because this is an ideal situation. Sharp bend like this, sediment is deposited here because it gets trapped, and it gets deposited here because it gets trapped. Now, I know what you're saying. I mean, we have plenty of ex-engineers in this room right now. No sane engineer would ever design a ditch that looks like this. That's the dumbest thing you'd ever do, right? Ever been to what's the Springdale Mall across from Bel Air Mall? There is a ditch that they literally put through between roads that does this. And every time I go, I don't go to that mall very much anymore. And every time I go there, I just look in the bottom because they're forever picking stuff up. And of course, sediment is whatever happens to be around. So we don't actually have like beautiful quartz sand sitting in the corner. We have shopping carts and leftover McDonald's wrappers and stuff. Sediment is whatever happens to be in the water. But it gets trapped here. And ultimately, what's going to happen to the capacity of the drain as the stuff builds up? What ultimately happens? It goes down, and as it goes down, what happens? All right, so you see the issue here now? When you start doing that, there are going to be complications unless you design it properly. This is a spherical object subjected to flow lines. This is a platy object subjected to flow lines. This has applications when you're dealing with things like docks or breakwaters on coastal environments. And this is an airplane wing. We're going to come back and talk about airplanes in a few minutes because the way airplanes work is the same way as grain entrainment works in flowing bodies of water, you'll see shortly. This is a critical diagram. It's got a lot of math involved in it, and if you were a physicist or an engineer trying to model how things are going to behave in a current, you'd be really interested in this. From a geological point of view, where most of us don't like math all that much, all you have to know is that there's two variables here. The one on the bottom, F sub g, is the force of gravity, modeled under these characteristics here upon a particle like so. This is the drag coefficient, or the force of drag. What you're looking at now is a grain that is sitting in a fluid. The fluid may be air, the fluid may be water. And what it's saying is that if you have this thing drop, there's a force of gravity accelerating in this direction, but there's the force of drag that is slowing it down, and they bounce off of one another. Now obviously in air, when you drop a particle, it's going to fall like crazy. But if this were a body of water, it would still fall, but it would slow. It would fall a little bit slower in terms of its overall distance. Depending upon what the fluid is, the fall rate will vary. Okay? And these are all the variables that are going to control what happens with that. So this is critical because this ultimately is what we're doing with grain size analysis through the method that we're going to be using. Since we are going to be doing grain size analysis, we should talk about the math behind this before we go any further. This is where we introduce Stokes' law. Stokes' law is one of the fundamental laws that geologists use, although it is derived on the basis of physics. Once again, this is modeled through physical observations of what happens with particles. This is Stokes' law. This is something that you do want to write down and understand what every variable is, because in an upcoming test, this is one of the things I often ask people to analyze and talk about. I will go over what each of these terms are, well, now basically. G is the gravitational constant, fixed at 9.8 meters per second square at sea level. Of course, the higher you go, the lower it becomes. The further down you go, if you're in Death Valley, it's higher there. The closer you are to the center of the mass of the Earth, the higher it gets. But it's considered to be a constant because, if you just stand at sea level where we are, it is going to be relatively constant. D, in this case in the relationship it's d squared, is the particle size diameter in millimeters. All right, it is possible to do things in imperial measurements or in inches, but why bother? Everything is much easier done with millimeters, etc. We have a couple Greek letters now that more or less relate to properties that are important and specific to the grains. This first one is the grain density. Now please note, it's the density, not the specific gravity here, but the density. The units are important when you're dealing with this. All right, so quartz has a grain density of 2.65 grams per cubic centimeter. This one is the fluid density. And again, it should be blatantly obvious to you. If you have a dense fluid, a grain will fall through a dense fluid much slower than it will through a very low density fluid. In fact, there's a point where if the fluid is more dense than the grain, what happens to the grain? It doesn't fall at all. Okay, so I wouldn't recommend that you start doing grain size analysis using mercury as your fluid. Mu, the last one, is the dynamic fluid viscosity. How many of you have had Connors in hydrology? All right, you know Darcy's law? Darcy's law is a very simple law. It determines flow rates through variably permeable substances and all. And all the stuff actually makes a lot of sense until you get to that one variable, the K variable I think it is, where it's basically whatever works. Kind of like you put everything else together, and if it doesn't work, you change that a little bit, and voila, it works, therefore you got the answer. This is what this is. The dynamic fluid viscosity is a catch-all where it's got a lot of different stuff in it, all of which is very hard to measure. That's Stokes' law. That's what we need to understand if we're going to do grain size analysis. Oh, and the last thing, of course, is the important thing. What does it tell you? It tells you the settling velocity. V for velocity, G for gravitationally induced. That's what the settling velocity is. What it ultimately says is, if you can determine the density of this grain, its grain size, the viscosity of the fluid it's falling through, know what gravity is, you can determine how fast this object of given density and given size will fall. That's what the settling velocity is. Through air. If you're doing it through water, then you have to put in different parameters for the water component here. That's Stokes' law. And if I had to measure every variable, if a geologist had to measure every variable, we wouldn't do it. I mean, we'd just say, can't be done. But geologists, if nothing, are clever and lazy. Clever first, lazy second. But let's consider what this all means. Number one, G is a constant, right? As long as you're not doing grain size analysis on top of Mount Everest, I think we can let that one go. So, as a constant, you don't have to worry about determining what it is. The density, not a constant. But consider where we are and what most grains are going to be. What was the density of quartz again? 2.65 grams per cubic centimeters. What's the density of clays? 2.7 grams per cubic centimeter. How about calcite? About 3 grams per cubic centimeter. Most grains that we would encounter along our part of the world have about the same density. And as long as we're not starting to do grain size analysis on magnetite-rich sand, doesn't that mean that the density is also going to be a constant? At least we're going to assume it is. Not true, but under most applications we can get away with calling it a constant. Fluid density. Not a constant, because fluids are different. But if we're consistent in terms of what we're doing, for example, if we only do grain size analysis in water, and if we make that water as pure as possible, and, this is important, if we're allowed to keep the temperature fixed or know what the temperature is, then why is that important?
Water changes density according to temperature.
All fluids change their density according to temperature. So if we keep our analysis at the same temperature range, say 25 degrees Celsius, which is room temperature, using only pure water and only water, then the fluid density also becomes a constant. Same with the dynamic fluid viscosity. If everything is consistent, it too should be a constant. When you're done, you're left with this relationship. Now, this is not an equal sign. It does not say that Vg equals some constant, which is the sum of all the other constants, versus the diameter squared. It means it's proportional to. And under these conditions, this is pretty easy to determine. We can determine the settling velocity based upon the grain size, if we wanted to. What we do in grain size analysis is turn it around. We can determine the grain size based upon the settling velocity. You got it? Now, the actual expression is not a simple linear relationship. It's logarithmic. With all these variables in here, there's some complications in here, okay? Now, this is ideally what you would predict. What this does is a plot of the log of the settling velocity in centimeters per second versus the log of the diameter in millimeters. The idea is that the larger the grain size, and notice here that this is no, I should point out, okay, because we've already talked about phi. Remember there was a scale, but remember that was to the negative base 2. This is normal log. So that's log 10. The larger the number, the bigger the grain size. Big grain size here, small grain size here. It stands to reason that finer grains will fall slower through a column of water than larger grains will fall. Or if you wish, the bigger the grains, the faster they fall to the bottom. Again, that's intuitive. So this is ideally what you would predict. In reality, this is what you get. This has been done a zillion times. This was done back in the 1920s and the 1930s when people didn't have anything else to do except model things. We have very good evidence to suggest that for the finer grains, up to about a grain size of about maybe half a millimeter or so, the actual fall rate follows very accurately Stokes' law. But once you get to the coarser grain sizes, it goes off the mark. Something happens for the coarser grain sizes. That's because coarser grains actually generate more turbulence. If you're moving faster through a column, the very act of the grain falling down will cause turbulence within the water. It's not falling laminar anymore, it's generating turbulence. And if the turbulence is behind a grain, what happens with the grain that's following it? It slows it down, so it's not falling at the rate in which you would predict, okay? Because of turbulence and grain, they call it grain interaction too. A grain might be falling faster than the one in front of it, and it bounces back up and pushes the other one down. It's just grain interaction and stuff like that. It's this thing again. This combination of these variables means that Stokes' law doesn't work for the coarser grain materials. And incidentally, you can see this all the time if you ever watch an airplane land. I actually like watching airplanes land. I like being on an airplane that lands because then it hasn't crashed. I have a real phobia about airplanes and all. But when I'm waiting for a flight to take off, I like watching because every once in a while you get this condensation trail, and this is classic. This is the part of the wing that is acting in laminar, going behind it. See the spoilers deployed down here? Actually, sorry, these are the flaps. The flaps increase the surface area of the wings, and you see why that's important, but they also generate turbulence behind. You can see the stuff coming behind. By the way, that's one of the things you don't want to fly behind in an airplane. You know, they got these really large airplanes. Has anybody ever you've been in an airplane, you get some turbulence? When you're taking off and landing, if you're flying behind the wake of another airplane, if it's a big airplane, there have been planes that have literally almost been turned upside down because they get caught up in that. It's the turbulence following behind, okay? So that's what's happening. Imagine this now as an airplane going straight down. Hopefully I'm not on it. And what you're dealing with now is turbulence behind it. Anything following behind is going to be influenced. You don't get a good straight fall. So this is reality. And the impact law actually works quite well with the coarser grain stuff. It doesn't work so well for the finer grain stuff because the finer the grains, the less wakes you're going to be generating. If only we could combine these two together. Be great. And divide it up into laminar flow versus turbulent flow. Be wonderful. Somebody did. That's the curve. And this is why I love science. You can model one part through one way and model another part through another way. Somebody came up with the idea of just saying, well, we'll just take two parts of it. It requires us to look at two different methods to do grain size analysis, but we can model grain size behavior based upon settling speeds if we use the so-called Ruby's curve. But what we have to do now is use Stokes' law for the finer grains and something else for the coarser grains. That's why virtually every type of grain size analysis that you use has a two-part component to it. I'm aware that many of you were working with Dr. Connors in terms of doing some grain size analysis last year. Did you use the hydrometer and sieve method?
Yes, sir. Yes.
You're not using that method here. You're using the pipette and sieve method. What's similar about those two? Two-part components. The thing you were doing last time, the hydrometer dealt with the laminar flow area, the fine grain size. The sieving dealt with this. For our method, we're using the pipette to deal with this, and the sieving still uses that.
Those hydrometers are a pain.
Yeah, well, I'll talk about some of my reservations about that method, as well as the reservations for the pipette and sieve method as well. Anyway you want to look at it, the really sucky bit is sieving. And no matter which method you use, you're going to be doing a lot of sucky bit stuff, okay? Now this is the enemy. Ultimately, this is what you're going to be dealing with. And let me talk you through a little bit how this is going to work. And then we're going to go into the lab a little bit later on. I'm going to show you how it actually works by actually talking through some of these different procedures. We're going to use a column of relatively pure water. We're going to take our samples and we are going to drop them in the column and time them. And the idea now is that since large particles fall faster than small particles, if we take a physical sample at certain times, we can get a sample that contains different sizes. But we're going to have to know what the temperature is. We're going to have to understand that temperature will regulate how fast particles will fall, because it's going to change the viscosity and the density of the fluids. All right? Now the trick to this, and the reason why grain size analysis is not exactly dealing with the most ideal situations, is that if we were to take a bunch of sediment and dump it at the top, we would have a problem. Because sediment's going to be a mixture of different grain sizes. If it's dry sediment, it takes a little bit of time for the fine particles to wet, get to the density they should be, to start to fall down. Moreover, they're going to be clumping. So we can't do that. In fact, we have to start off with a wet sample. Part of the grain size process is to take your sample and break up all the particles in their smallest disposition. They're going to be in a water base already. So instead of actually dumping the sediment in the top, what we do is we put the sediment in the columns and then agitate it. We use a simple plunger device. Basically, you keep the column moving, and then when you get to a certain time when you want to start timing things, you stop. Now right away, you should see what an issue is with that. If you're using a plunger to move things up and down, up and down, up and down, what are you doing with the water column? It's in turbulence. So when you stop, half the grains are probably moving up, half the grains are falling down. That's not exactly ideal for determining grain size distribution, right? But as long as everybody does it exactly the same way, and this is important for these empirical ways of doing analysis, as long as you do everything exactly the same way, then your data will be comparable to everybody else's. Now, to those of you who've done the hydrometer method before, you cannot compare the pipette method to the hydrometer method. It's two totally different systems, like apples and oranges. You can't say how good an apple is if you're eating an orange. You get the same results, nutrition, but you're not going to have comparable data. All right? So that's the first thing you need to know. By the way, there was a change, and we do have standards. There's a listing of standards for people to follow the same methodology. About 5 years ago, they changed the whole process. They didn't change the process. You still have to use that agitation, but the last thing you do to start the clock is to take the column, put your hand over one end, tip it upside down, and when you're ready to go, flip that back up. I refuse to do that, because I've never done that before. And if you do that, what does it do to your data? Makes it non-comparable again. I'm more interested in comparing my data to my data rather than actually, following the rules. If I were doing it for somebody else, and I do a lot of well, not a lot anymore, but I do some contract work for grain size analysis. Someone comes in and says, want to do grain size analysis? You want a hydrometer sieve or a pipette sieve? If they do a hydrometer and sieve, I'll ask them, do you want it to follow the EPA or the ADEM rules, or do you want them to be consistent with data you looked at previously? And that's important. Okay? So the idea now is that what we're going to do is suspend the sediment, and then we are going to take a physical sample after a certain period of time. Now, there are two tests you have to do, or two runs you have to do. The first is going to be done that will sample the silt and clay fractions in your sample. At 23 degrees Celsius, if you agitate a column and stop, exactly 4 minutes and 28 seconds later, by modeling, you can determine all the sand, and that's the content that is down to about 63 microns in diameter, have settled at least 10 centimeters down into the column. The gravel's already down here. The coarse sand is already down here. And all the finest sand has made it to 10 centimeters down. If you take a physical sample at 10 centimeters at 4 minutes and 28 seconds and pull it out, what you'll have is an aliquot that is full of sediment, but only silt plus clay. You got it? And that's done based upon our understanding how the settling velocity actually works. If the temperature drops, by the way, the density goes up and the fall rate slows. So Mary, when we were doing yours yesterday, that was 21 degrees, it was 20 degrees, it was 48, right? A simple matter, we did some stuff for Mary the other day. At 20 degrees Celsius, it was 4 minutes and 48 seconds. You lost 20 seconds. You already had to wait 20 more seconds for the finer sands to fall down. The warmer it is, the more dense it gets. Now, I've got a range of different things for you to use in terms of temperatures, but it's absolutely vital that the temperature in that room, the SED lab, is consistent. It might go up a little bit, it might go down a little bit. But if the temperature drops below about 19 degrees Celsius, you're not going to be able to do it. If it rises above 25 degrees Celsius, you're not going to be able to do it. So that's why we have to have a very strict temperature range. So rule number one, don't monkey around with the thermostat. I don't care if you're freezing. Put on lab coat or something, okay? Don't muck around with it, especially if the run has already started. That's the first part. All you're going to get now is a sample suspended in fluid that consists of silt plus clay. At 23 degrees Celsius, exactly 5 hours and 43 minutes after you agitate that column, all of the silt has fallen at least 7.5 centimeters down. Now, it takes a long time for this to occur because silt goes down to 4 microns. So it takes a lot longer for silt to settle back down. If you take a sample at 7.5 centimeters down, 5 hours and 43 minutes later, what you've got is an aliquot that contains only clay. Now, you see where we're going with this? If you have a fixed volume of fluid with only clay in it, and a fixed volume of fluid with clay and silt in it, you can determine the percentage of silt and clay by simple subtraction based upon those aliquots. That deals with the Stokes law component of grain size analysis. All the sand that's fallen down here, all the gravel that's fallen down, you can't use the pipette, you can't use the hydrometer method to do that. How do you do that data, or determine those data? Through sieving, which is the really crappy part of this whole process. All right? Now, in order to make this work, you have to have a fixed volume of water within the columns. That's 1,000 milliliters. You also have to know the starting weight of your sample. That's the first thing you do before you even start processing things. You've got to be able to take those sediment samples after they've been weighed and break them up to the finest clay and sand particles that are in there without literally grinding them up. Never, ever, ever grind a sample for grain size analysis. Never bake a sediment for grain size analysis, because baking causes the clays to shrink, and you could actually make larger clumps of stuff by doing that. Air drying is always the best thing. And gradual shaking to break the particles up is a good idea. And it's always a good idea to add some sort of a mixture, a soap if you wish, that will promote the breaking up of these clay particles. All that is the preparation stuff that you have to do for grain size analysis. Once you get the particles all busted up, you put them in the columns, and you do your analysis. Now, I talked about the idea that there's two methods for this. The real hassle with the pipette sieve method, which kind of sucks, is that if you're going to be extracting a physical sample, you've got to weigh it. You're weighing something that is in a fluid. You've got to get rid of the fluid. You've got to make this as fast as possible. The best way of doing that is to take that fluid and pass it through a filter that's got micro pores in it. The filters we use are about half a micron in diameter. The idea is the fluid passes through it, all the sediment that was in that aliquot is left behind in the filter papers. In order to make that work, you have to have filter papers. They're not cheap, by the way, so go easy with them. You also have to have some sort of means to draw the fluid through as quickly as possible. Vacuum filtration is the way to go. But the real issue is you got to have those filter papers, and they got to be pre-weighed, because you've got to weigh them before in order to determine how much the weight is after. And you're going to have to heat up those filter papers at lowest temperature. I don't care if you bake the clays now, but you need to dry off all the water that was contained within that aliquot. And because you're going to be heating the filter papers up to weigh them, you have to follow the same methodology to start it. So you weigh the filter papers blank after you've heated them. You do the analysis, extract the different components from it, and I have a spreadsheet that will automatically do it for you. And then, of course, the last thing you have to do is figure out what the grain size of this is, and that's got to be done separately. You've got to sieve out the material and put it through a sieving process as well.
Is this a gravity funnel setup, or is it like a Hirsch funnel or something?
No, just a standard vacuum filtration. Same type of thing that you would do if you were measuring E. coli content in the atmosphere. All right, it's the same type of thing. We use that. That's why the filters are expensive. A box of 100 filters goes for $60. So we ask you to be a little bit aware of the cost involved in that, so don't go stuffing around. I'll show you how you have to set all that up a little bit later on. Okay? Sand and gravel, we will use sieving for. You have to extract all the sediment out of the columns, dry it, and this you can put in an oven that's fairly hot. The sand will dry, and then you put it through a stack of sieves, which is what I really hate. Because again, you have to follow statistical methods for this. 15 minutes of sieving is required for each sample. I do a lot of grain size analysis. In fact, I was trying to figure out how many I've done over my lifetime, and I'm probably at 15 to 20,000 by now. As I say, I do a lot of it. By the way, when I do it for consulting basis, I charge $45 a piece. So you can make a lot of money doing this if you want to. But I would give it all up to avoid having to do sieving. I really, really, really hate that. In order to speed things up a little bit, I've actually made one of our sieve stacks divided up into 3 sieves. So you can do 3 samples at a time, which works quite nice. It gets through it a lot faster. If you're wondering, why are we doing the pipette and sieve method? Because it does seem like it's got a lot of work. There's two benefits, I think, to pipette and sieve that the hydrometer method does not really allow you. Number one, the hydrometer method requires you to come in and be here virtually on call for 24 hours. You have to start your samples with pipette and sieve, and then 6 hours later you're doing the second run, but then you're done. And within that interval of time, you can do other things. But the hydrometer method always bothered me because every 5 minutes you're going back and taking another reading, and frankly, I don't want to come in at 3 o'clock in the morning, damn building's locked. You know, I just don't like it. But you don't have to do all that pre-weighing stuff. And the hydrometer method gives you those data that you need for doing the statistical analyses because it allows you to come up with a curve. This gives you physical samples. The other thing I don't like about the hydrometer method, never have, is I don't think the hydrometer method is particularly accurate. Now, those of you that did this before, you know, when you put the hydrometer in, you got to read the scale. Well, you know, for accuracy, you should be getting to 1/10 of a division, but you can't read any closer than about half. And there are times, I swear to God, the density's gone up after a while, and if you put that into programs, the density goes up, it just throws everything out. So you have to fudge your data to get it to work, and everyone's done that. I mean, don't take that as a criticism. It's what's required by ATEM. They only accept that for doing analyses for environmental things, but I just don't like it.
Our biggest problem with the hydrometers is they would bounce and start bouncing in there. You know, you have to like calm it down.
And when you start bouncing, what you're doing is you're suspending things too, and that's an issue. So you have to be very careful how you put it in. There are things called micro hydrometers, but we don't use them very much because they're expensive. Ultimately, Disadvantage also I find for the hydrometer, this is the reason why I started doing pipette and sieve for where I am. The pipette and sieve method is very sensitive. You can measure clay contents in a sample down to a fraction of a percent. For the hydrometer method, anything less than about 5% clay, I think, doesn't read at all. And you need big samples. What was it, 30 grams or something for hydrometer? Yeah, all right. For the pipette method, I've done grain size analysis on samples as little as 3 grams and got decent results. Now you should realize, okay, the less sediment you have, the more potential error you're going to have. That's true with all methods on this. So there are issues with both methods. And ultimately, when you're doing this, the real problems are going to be in how inconsistent you are with the procedures. It is possible to make mistakes. Mary can attest to this. What did Dr. Haywick do yesterday in the lab when you were talking to him? And Dr. Haywick made I made a couple mistakes, which is embarrassing, especially when someone sees you doing it. But you know, it just happens all the time. So just be careful, okay? We do not do gravel separations in this process because, frankly, if you're doing grain size analysis with gravel, like one big pebble falling through a column is not going to give you anything anyway. So. Okay, and the actual analysis, this is what's nice is when you actually come up with your data, you can actually determine what things are very simply using Excel spreadsheets. This is the sheet you're going to be using. In fact, this is the data sheet you're going to be using to actually enter the data. What you do is you put your sample number up here. You put your dry weight, what it weighed as before you put in the bottles, and then this gives you all sorts of information. This is the weight of the filter papers before and after, and this spits out all the numbers that you need in terms of things like histograms. The spreadsheet also will produce the important stuff like the percentages of everything. You're going to have to fill in this stuff yourself down here. What I'd ideally like to do is actually have the computer do this for you itself, but there's a problem with Excel. Excel was never designed for scientists. You can have pie charts and all manner of exploded things, which is really great if you're trying to sell a condo in Sarasota. But if you're doing science, it does not have the ability to actually put out ternary plots. And remember, ternary plots are how we determine what the grain size is. So you're going to have to do this manually. It's kind of a good exercise, but it's a pain in the butt as well. You'll have to enter these data down here yourself afterwards. And notice there's a line for Folk and Shepherd. Might as well get in the habit of using both of them now here, okay? There will be a ternary plot that is put out. A long time ago, I guess I sent out a plea to anybody in the blogosphere if anybody had a routine that would do Excel ternary plots. And somebody from David Graham, who I actually met a little bit later on from the University of Wales in the UK, sent it off to me and said I was free to use it, and I told him it was only going to be used for teaching purposes, which it is. It will automatically plot up your data in this fashion. Unfortunately, Excel does not allow you to individually plot out what these are. So you're going to have to find out which ones are which and determine what it is. And then I have an overlay, which is in the package of stuff I gave you earlier for Folk and for Shepherd. You put the plastic overlay on this, find out where the plots are and those things, and determine what it is, and add that manually to the data sheets. You'll also have the histograms being plotted out as well, okay? This will work automatically for you guys when you do it, okay? Okay, real fluid flow and entrainment. Entrainment literally translates into getting sediment to move. As you should all be aware, there's a certain amount of inertia. A particle or an object that is not moving requires a little bit more oomph to get it moving. And it also requires a little bit more oomph to get it to stop moving. All right? That's one of these laws of inertia. But fluid flow, under ideal situations and realistic situations, will explain how grains have, in some cases, an advantage if they are shaped in certain ways. That will get them moving. It will also lead us back to some of the traction movement patterns that we were talking about. It will also explain how airplanes ultimately fly. If you are not a follower of aviation, this is the new Dreamliner, which everybody is thinking is going to be one of the greatest airplanes probably ever made. The only problem is it's made of plastic. And I don't know about you, I've flown enough now that I'm borderline terrified of flying, which is one of the reasons why the first thing I do when I get on an airplane is drink about 5 drinks. Then it doesn't matter so much.
The landing gear doesn't come back down on that one.
There's a lot of problems with it, but it's a newer generation airplane. But mind you, the super jumbo jets Airbus puts up, those things have some real issues. They just found wings that are cracking like crazy now too. So engines blow up, wings crack. Oh, it's wonderful to fly. And I'm going to Australia later on this year, so I'm going to be on probably one of those larger ones. I want to do it, but I'm also terrified to do it. Anyway, getting back to how airplanes fly and all, it's the same thing as how grains get moved in the first place. So let's consider ideal situations. And again, you have to think of this as being ideal because there's a lot of variables that are going to control things. So once again, we're talking now about grains sitting down on the bottom of a substrate, say water or some fluid moving in that direction, and there's your grain sitting there not moving at all. It's in a resting state. If you look at how water moves in terms of a laminar pattern, okay, so again, flow lines do this, etc. And remember that profile which has a little bit of a bend in it once you get down to the water. What happens is if there's an object that is a barrier to that ideal flow line, it can still behave in laminar fashion, but what will happen is it will have to divert around the grain, either like this or around it like this. Now notice there's no ability for the flow lines to flow underneath the grain because there's a barrier to it in that direction. Now what you're going to notice is that flow lines that have to flow over an object that has a shape like this start to get a little bit compressed. All right, and that's what's kind of, it doesn't show it as well here, but it kind of shows you how it goes over this grain here. That is just the velocity vectors. Notice there's a little bit of disturbance in through here, a little bit of turbulence, ultimately giving rise to something like this. This is an important and a very well recognized pattern of flow that does pretty useful things to us. And now we're going to switch to airplane wings because the same type of thing happens with wings. A cross section of an airplane wing looks like this. In fact, the design of airplane wings is one of the most top secretly guarded secrets. I'm not saying that particularly well. It's something that airline manufacturers don't share an awful lot of. When you get a new idea for a wing, it's really something you don't want to advertise because it allows the airplanes to fly, and the more effective way of lifting the airplane into the air, the less fuel you're actually going to be used. So here's what happens. Flow lines come like this. They get compressed along the top. I'm going to exaggerate this a little bit so you can see what I mean. It's not nearly this much. And then along the bottom, they're not really disrupted all that much. When you start getting compression like this of your flow lines, that basically generates a low pressure system just above the airplane wing. It's high pressure down here. It's not really high pressure, but it's just basically the same amount of pressure, low pressure here. Literally, the wings, when they hit a critical speed where laminar flow is going over top of them, will start to lift up into the air. In fact, if you've all flown at least once in your life, I guess, right? Has anybody ever flown on a really big airplane? Like a 747, something like that? Did you watch the wings when you're taking off? Oh, next time you do this, you got it. It's the coolest thing. All right? Imagine you're in a 747, one with the wingtips or something big. When you're taking off, the wings are like this because they're full of fuel. If you're going across the Atlantic Ocean, the Pacific Ocean, you need a lot of fuel. So they literally are like this. And when you're moving down the runway, they're doing this because they're just bouncing like crazy. When you start to build up speed down the runway, something wonderful happens. You see the wings start to do this. Come up. Before you take it off, they start to come up like that. In fact, I watched the 747. I estimated the wingtips probably lifted 10 feet into the air. Then all of a sudden, up goes the airplane. Literally, the wings pull the airplane up into the sky. That's exactly what happens here. If you have a grain that has a round shape to it, a low pressure system is generated here. Next thing you know, the grain gets lifted up into the water column. But there's a problem. Grains like this are not designed like airplane wings. The airplane wings stay up there because of the difference in the shape. A grain like this, once it is here, what happens? The lift here is countered by the same pressure down here. What happens to the grain? It loses its lift, it comes back down. But by this time now, you have already been subjected to the force of drag. So the grain goes up like this, is moving that direction, and then down it comes like so. Sits there for a little while, moves up again, and goes like so. What are we demonstrating? What is happening? What is that motion called? Saltation. So saltation is a response to the lifting of grains, okay? Now you should also be aware that there's a whole bunch of other things that can happen in terms of how flow works. This has been modeled, as I said, extensively by physicists. We don't have to worry too much about it. But I do want to say this, that those of you that go a little bit further in graduate school, when you start talking about things like Reynolds number is used to model how turbulent water flow is. And anybody who goes into, say, modeling how rivers flow or how to modify rivers has to take that into account. The more turbulence you have, the higher the Reynolds number is going to be. The higher the Reynolds number is going to be, the more potential you have for erosion, because turbulent flow is going to cause all manner of things, okay? So there's a lot more to it than just this. From our point of view, though, we're asking ourselves, how do you get a grain moving in a column of water in the first place? Now, question for you. If you had two grains, one a round quartz grain and one a chunk of biotite, which one's going to get lifted? The round one, okay, not the biotite, it's flat. This is going to have less of a disturbance for the flow lines. This is less likely to move where that is. Ever been to a beach and watched the sand grains rolling around as water's coming and going? What happens to the bicas? Boy, there's a combination of things. What happens to the micas, the biotite and the muscovite? What do? They stay behind because they're not getting the lift they need. And incidentally, that's one of the reasons why when you look at beach sediments, you'll often see alternations between quartz sand and little layers of biotite. It's because of this difference in terms of how they are lifted, okay? Real important stuff. All right, now let's talk about what this all means now. So this is a diagram that shows you more or less what's happening with entrainment. These are graphic representations of mathematically modeled stuff, because all this stuff can be modeled. That's what engineers do. Engineers are very good at doing this, by the way. They model exactly what will happen to an airplane wing given the amount of weight on board the airplane. And if they are doing the job right, they can estimate exactly when wings will fail. And by the way, if you like airplanes, there was a really good program done by Nova about 10 years ago about the 777s. They built it and they showed this plane that they were testing to make sure that they understood how the wings work. The engineers predicted how much upward force it would take for the wings to fall off an airplane. And they did this by putting the fuselage, making a real airplane. Everything was complete with the engines on it. And then they started lifting the wings up, increasing the torque. And they estimated that when they get to a certain amount of torque, the wings would crack. It happened exactly where they predicted it. They were very happy about that. Because the problem is if an engineer gets it wrong, if they well, you know what's going to happen if they get it wrong if it's too weak. But if they don't understand how the wings work, then they will not be able to determine how much turbulence you can take, and more importantly, how much weight you can put in the airplane. Okay? I've been on airplanes where someone comes on, and this is scary. When you're getting on, especially a small airplane, and the pilot comes up and sees all these people loading up oxygen tanks from a dive trip, and he says, "Did you tell me you had these on board the airplane?" And they go, "Yeah, no worries." And I'm getting on the plane with my little duffel bag of dirty underwear, and I'm going like, if we're heavy, we're not flying. It's kind of scary. Anyway, changing the subject and going back to something that's more relevant to what we're dealing with today, these are diagrams that are showing you how sediment should move based upon modeling. There's two relationships here. One is with Shields, 1936. We're going to talk about Shields' diagram in a second. What it does is it shows you the relationship between grain size in a logarithmic fashion. Okay, remember this is not linear, this is logarithmic. Grain size, where it's increasing in this direction, versus the velocity to move the grains. That's the shear velocity here now. So this is basically the amount of water flowing over the sediment. And what it shows you is the difference between where there's no grain movement and where there is in fact movement. So everything above this line is where grains would move. And there's no surprises here. You would predict that you would start requiring higher shear velocities to move grains as the grain size increases. You should also anticipate that as you get into finer and finer and finer grain sizes, it's going to level off, because it really doesn't matter if your particle is 1/100th of a millimeter or 1/50th of a millimeter. The velocities are going to be fairly similar. It doesn't take much to put particles like that into suspension. This diagram here, which was done in 1966, based on modeling in 1966, is the transition from traction to suspension. So the idea now is that there's going to come a point for every grain that it's going to stop rolling along the bottom or sliding along the bottom in contact with the bottom and be carried in suspension. There's no grain movement. This is traction. This is suspension. Or if you wish, This is entrainment, where stuff is actually moving. Now I mentioned Shields. This is Shields' diagram. This is that nasty empirical diagram I told you about. Now Shields' diagram deals with the engineering, if you wish, of how sediment moves. That means every variable is plotted up here. The boundary Reynolds number, that has to do with the amount of turbulence and shear. It's cut off, incidentally, at the bottom. Has about 4 variables in it. I don't even know what they are. And this, I have no idea what this is either. Because this is designed to show you all the variables that might happen with grains. But ultimately, it is still empirical. Does anyone know what empirical data is, or what empirical relationships are?
Data that's been derived from calculations.
Yeah, but it also is done on the basis of observing reality. So what they do is, they'll do an analysis where the variables will plot right here. So they measure all these things and plot it right there. They'll do another one where it's here, and another one where it's here, and here, and here, and here, and here. And then they will determine that this particular one, there was movement, there was entrainment. But this one, there wasn't. So it's not like they are actually modeling a line that shows you where the true movement is. They take data in a shotgun approach, plot it all up, and they say, in general, everything above here involved entrainment, everything down here involved no entrainment. That's empirical. All right, so what you're looking at here is not something that's going to show you right down to the smallest variable what's going to happen, because this is in some ways driven by way too many variables to adequately model. Now, if you like this approach, this is a really good way, an engineering way, to determine when sediment will move. A more practical way, if you're doing it empirical wise anyway, why not just do the stuff that geologists actually can measure easily? Why not measure grain size versus velocity? That's the same type of thing if you think about it, right? You take a whole bunch of sediment, you put it into a flume, you put a current over it, and you observe, does it move? If it moves, then you say it's moving. If it doesn't move, it's not moving. And you plot all those data up here, what you end up getting is a fuzzy zone. Everything above the fuzzy zone is going to move. They use the term erosion here, but that's entrainment. Everything below the fuzzy zone doesn't move. But if you're right here, sometimes it moves, sometimes it doesn't. It's not a sharp line, it's a fuzzy interval, okay? So as long as you're not in this area, you're fine in terms of things. And this is something we can move. Once again, in general, it makes sense. The coarser the grain size, the higher the velocity you need to move things, okay? That makes sense. Observe down here, though. When you get to this point, it either goes flat, and you'd expect it to go flat again, because once you get into really fine grains, it doesn't really matter if it's, as I said, 1,000th of a millimeter or 100th of a millimeter. It's going to be about the same current to move. But look what happens here. In some situations, it takes as much current to move the finest particles as it does to move particles that are 200 millimeters is 20 centimeters in size, like this. Why?
When you have like superfine clays, don't they have an electrostatic?
More or less, yeah.
And then, you know.
Exactly, right? Now, it says consolidated here. Consolidated is a term that can mean it's lithified. It's not lithified. We're not talking about actually moving shales or anything like that. But, as Kurt was saying, clay particles, which are platy, require more current to move them anyway because they don't have that liftability, but they also have uncharged, or they have a charged excess where you can have some things clinging together. In fact, this is one of the reasons why in some situations you will find very well sorted sand with big chunks of clay within them. We call those flat pebble breccias. They're absolutely diagnostic of a particular environment. An environment where clay has been sitting out for a while usually involves a little bit of drying. So there's a little bit of drying of the clay, and then when the currents come in, what happens is the clay sits there and sits there and sits there as the currents increase. The sand is moving, but the clay isn't going. And then all of a sudden what will happen is there'll be a bit of a boil. Some of it will break up, and you're moving big chunks of stuff relative to the sand in big clumps. Later on, you get a mixture of very well sorted sand and these flat pebble breccias. Now, what kind of environment would you expect to see periodic evaporation periodic drying of clay with currents coming in periodically as well. There really is only one. Not a floodplain, a tidal flat. See, a floodplain, what happens is when the stuff dries, it gets plants in it, it turns into stuff, all right? It's got to be a place which is wetted and dried where there's lots of clays. There's only one place where that happens, a tidal flat environment. So you see something, a mixture like that, you know you're dealing with a tidal flat overall. So diagrams like this allow you to model things, but they also are important for more or less explaining what we see in the rock record. Now here's the diagram that we're going to use as a summary diagram. We've talked a little bit about how sediment can move. We talked a little bit about how increasing currents will move larger sediment with some limitations. This diagram summarizes several of the other diagrams we've seen. Here's Hjulstrom's curve, okay? So there's where the diagram comes up for the stuff, the clay that is kind of consolidated. Here's where it doesn't. Also on this, what they've done is they've taken out the fuzzy zone and have tried to indicate that there's another variable you have to take into account, all right? We haven't done this yet. But most situations where we live, it's quartz is the dominant coarse grain material. Not always. So here what you're seeing is different lines, and again, don't assume these lines are accurate, okay? This gives you an idea where, say, the average is going to be. There's quartz, there's amphibole, there's magnetite. Why does it take more energy to move magnetite than amphibole, and why does it take more energy to move amphibole than quartz? What's the difference between those grains? Their specific gravity, okay? The heavier the substance, stands to reason the more energy it takes. This is important because when you start looking at sand and starting to separate it out, it's not unusual to see in a beachy environment a whole bunch of quartz grains of one size and some smaller grains that happen to be composed of amphibole or magnetite, because those are the ones that are stable, moving in conjunction with the larger quartz grains. Anyone got that? And it stands to reason again that there's going to be a difference in terms of where the grains pass from being in traction to being in suspension. Okay? So that's the important stuff. Now this is another diagram I want you to be aware of, because here you can actually start using some things to predict the behavior of particles as well. This is empirical. It's not meant to be an absolute diagram, but it allows you to get an idea of what kind of conditions, energy conditions, were around when sediment was being deposited. So down here, there's clay-sized particles, there's silt-sized particles, there's the sand, and here's the pebbles and gravel. Here is increasing velocity. No numbers, okay? But it shows you now the relationships between getting sediment to move initially and ultimately things like the settling velocity. That's the boundary between entrainment and deposition. Okay, so that's basically Hjulstrom's diagram. That's the boundary between traction and suspension. That's Graf et al.'s diagram previously. So they're superimposed on this. How does it work? Suppose you identify a particular grain size of sediment. It would have to be something that's ideal, so only one grain size is permitted. That's your grain size there. To determine what the entrainment velocity is going to be, how much energy it takes, how much movement it needs to move initially, you draw a line straight up like this, where it intersects the entrainment curve, you project laterally and measure what the velocity would be here. All right, got it? So the coarser the grain size, the higher the settling velocity. Doesn't work so well down here because anywhere along here, anything below about sand size is going to be about the same thing. In fact, we've known this for the longest time. Silt doesn't really need much currents to be moved around. Okay? To pass from traction, like rolling or sliding or bouncing along the bottom, to suspension would require a significantly higher velocity. In fact, it would be whatever this is up here. Okay? Now we can again model that quite nicely in things like flumes. If the currents stop entirely, the grain will eventually fall back down to the bottom. That's the settling velocity. And please note, the settling velocity is at a lower velocity than the initial entrainment velocity is going to be. Because again, you have to overcome a certain amount of inertia when you're dealing with things. That ultimately is what we measure when it's doing grain size analysis. All right, so there are means by which you could do analysis of sediment and determine approximately what was going on in the past in terms of currents. but there are other variables that have to be factored in this as well. And really, you know, the only way that you can fully understand how sediment works is to model movement under the most ideal conditions that you possibly can. That's usually done in a flume. So, we have a flume back there. That flume was built by a student as a summer research project several years ago. We're going to use that flume and a little bit later, and I'm going to let you turn the currents on, put some sediment in there, and just watch what happens ultimately to it. Have some fun with it. That'll be one of our activities. An activity is where we sit around and during the lab, you sit down and model it, and then you report your observations, give it back to me that day. So it's kind of like an abbreviated type of lab. You work in groups for doing something like that as well. So that's the most ideal situation we can deal with, okay? And really, realistically, as you see, there are more variables that we just can't control. This page, because now is the time that we have to start getting into this routine of knowing what's due and when things are due and what we're going to be doing, okay? Your second writing assignment is due Thursday by 5 o'clock. But if you can get it to me earlier, I would greatly appreciate it, because that's going to be peer reviewed. This is the first of your peer review exercises. That writing assignment will be a combination of what your grain size hypothesis is and the methodology that you're using to do this project. Now, first of all, the hypothesis. I have talked to most of you about what it is you're doing, but not all of you. This time, you guys, a lot of you were working so diligently, I found out you had samples when you called me at home and said, how do I get in the SED lab? I was not expecting that. So I have not talked to some of you about what your hypothesis is. Remember, a hypothesis has to be done in a testable manner. So, let's see, Ron. Okay, I know what you did because I was out there coring with you. You're looking at evidence of flooding events in core sediment taken at the base of a delta. Your hypothesis should be worded as follows. Evidence of flooding events will occur as sand beds within an otherwise fine-grained deposit. You see what that is? It's stating a fact. That's your hypothesis. You also have to tell me what tests you're going to do. For all of you, the testing will be the same. I will use grain size analysis to determine this. That's a hypothesis. That's the test. And by the way, if you were a biologist, this is how they do a lot of their research. They would write this up in the following way. HO is the hypothesis. Grain size, flooding events will occur as specific coarse grain sand beds in otherwise fine grain sediment. And then down here, the test, grain size analysis, 5 samples, whatever. That's the first part of this writing assignment. The second part is the methodology. How are you going to do it? Now, we haven't talked about methods yet. I've gone over a little bit of what you're doing here. You're going to see how to do it in the lab. To be honest with you, it's probably unfair to get you to all start writing this thing up because, frankly, you know what? You always go into too much detail. I did the following, I did this, I did that, I did everything. So let's see how we can actually make it easy for everybody, including the peer reviewers. Oh no, just leave it alone. If you come to our webpage, and I'm sure most people haven't done this yet, down, why do they go? Oh, here we go. If you come down here, you will see all the assignments where you can link to them if you ever lose your package of stuff. Down here are the major projects. If you click on the grain size project, it will tell you ultimately what you're in store for the final product. But I give you examples of certainly what you need in terms of links and stuff, but I also give you examples of what I'm looking for. There's an example of how the title page should appear. There's an example of the abstract. And here is an example of the introduction. Oops. And an example of the methods. I don't encourage plagiarism. But if something's already done, there's no reason why you can't acknowledge someone doing that. I encourage you to borrow directly this paragraph. And notice, see, this is why something like this is a good learning exercise. This shows you the main things you have to do, etc. here. And you might want to modify this, by the way, because if you did 15 samples or 20 samples, modify that. But it goes over what was done, and then it comes down here. Grain size analysis was done using the pipette and sieve method according to the procedure outlined in the very document that's in your package of stuff. Anybody's interested in reading how you did it, they can go look at it. There's no sense telling me that you kind of put in 4 grams of sediment into a column, agitated it, waited 4 minutes and 38 seconds. I mean, that's all in there. So that will cut down the amount of methods you have to write. But there is one thing you do have to add to this. Methodology is not just what you do in the lab. Methodology is also what you did to get the samples. And that's where it's individual for all of you. Those of you that collected samples in the field with a shovel, make sure you tell us how you did it. He put them in plastic bags and brought them back to the University of South Alabama. If you did a core, say that you extracted a core using the piston coring method, something along those lines. If you used a kayak to get your sample, saying a kayak was deployed to collect X samples from the bottom municipal park. And then you can go into this saying, from this point, samples were processed, and take it verbatim from there. Okay? Now the peer review process. And here's why I wish I'd actually changed the due time for this. And if you get this done before 2 o'clock, if you get it done at the start of class, bring it into the start of class, because with peer review, I'm not going to be the first person who sees this. I'm going to take your assignments and give them back to you. The peer review components, this is again is your package, you don't have to print this off, but there are peer review forms here, and I just want you to see this. What is that? Why? It's a simple PDF file. Why is it doing that?
Well, load it so you can view it.
Okay, you guys will get caught up in the lab on Friday. Those people are going to physics, I understand, go, so just take off. I think we have a problem. I've never seen it do that before. The peer review forms that are in your package is a form. I will give you back one of these things that is the methodology and hypothesis to review. If you're in a group, this is important, okay? If you're in a group, I want every member of the group to write up their stuff independently. So even though you're doing the same hypothesis, the same methodology, write it up separately, because each one of you needs to be reviewed separately. And you may find that if you all do it slightly different, there'll be one version that's really good. You can use that for your final, for the submission for this later on, okay? But I need to be able to give you a mark for this individually at this point. The peer review will work like this. If you get me your assignments in, as I said, preferably as early as possible on Thursday, I will distribute them back to other people in the class. So Patrick, if you give me yours, I might give yours to, I don't know, Angelique. Angelique, you'll use your peer review form, which is peer number 1, to review Patrick's submission. Feel free to do the actual additions, editorial things on the paper directly like I did for the thing I just gave back to you. You give it back to me on Friday. All right, so I need it back as quickly as possible because I still need time to look over these and get them back to you on Tuesday. This is what I mean by rapid turnaround, okay? So the sooner you get these to me on Thursday, the better it is. I am obligated to actually waiting until 5 o'clock Thursday for some of you, okay? I'm aware of that. If you get it into me at 5 o'clock on Thursday, I will not be able to give it back to people in class because they're already gone. So the way it's going to work is this. I will redistribute these assignments for peer review as quickly as I get them. In general, if you give me yours at 2 o'clock on Thursday, and you give me yours at 2 o'clock on Thursday, I'll swap them around, and you're both walking out the door at 2 o'clock on Thursday. If you give me yours at 5 o'clock on Thursday, you're going to have to come to my office first thing on Friday so I can give you one to review because I need it back by 5 o'clock that Friday. Does that make sense? Now you know the perils of doing a W course, because again, we need to go quickly on this, but I need to follow the rules that I have to do for these writing courses. Oh, there it is. Wonder what it was doing. The author name will be whoever it is you're reviewing. I've already done the assignment title for you, the due date, etc. Reviewer information is your name, the date reviewed, and this is the only thing you have to do on the form is, was it easy to read, minimal spelling mistakes, etc. And I would like you to more or less give an overall opinion of the quality and give it a grade. What would you give this person a grade? And I will not only review your paper as well, I will review your peer review. And you're going to get a grade for how well you reviewed, and I will give the paper a grade as well. So a lot of feedback. We're going to do this 3 times this year. This one shouldn't be too bad because there's not going to be much stuff in there. Okay? That kind of makes sense? All right, now for the next couple of weeks, we're doing grain size in the lab. I'm going to give you a bit of a breather now because I've been talking a long time. I'm going to go and use the facilities, grab myself another cup of coffee or something. I'm going to ask you to meet back here in about 10 minutes, 5 or 10 minutes, say around 12:30. We're going to go in the SED lab, and I'm going to talk you through the various stations that we need to use for doing grain size analysis, okay? Those of you that want to get a good start on things, now is the time to start prepping your samples, because all the stuff I told you about doing, there's different steps along the way. And I highly recommend, if you haven't already done so, to read the lab manual that's in the package of stuff I gave you, because you need to know that when you start grain size analysis, from the day you first start weighing your samples, the earliest you start doing grain size analysis is about 4 days, because each step requires a certain amount of waiting time. And we are going to run into a problem here. If you have to start at one point and come back about 5 hours later to do your next samples, that means you have to have a window of opportunity where you're clear this time and clear about 5 or 6 hours later on. That may be difficult, which is why we're going to be doing 20 samples at a time. Since each of you have done 5 samples each, that means there should be 4 people doing a run at any one time. Learn to cover for each other, prep for each other, and I'll show you how that's going to work too, okay? If you each help each other, it makes the lab go more efficiently, and it makes it ultimately everyone having a better time. Okay? See you in 10 minutes. So, a couple things to note. Whenever I do writing, my writing is atrocious, I'm aware of it, so I see you already squinting and all. Come see me if you don't know what the comments are, or if you cannot interpret the comments based upon the following summary of what I read in general, okay? Number 1, the thing to note about the abstract, introduction, and conclusions, they do an awful lot of overlap, but they are all unique in so many different ways. Number 1, the abstract is a concise, albeit brief, summary of the contents of the entire paper. Many people actually kind of floated around with that idea, but the abstract should be self-contained. It's not, as most people said, meant to decide whether the reader wants to read the paper or not. That's what the English people tell you if you're looking for something for research, for building up a term paper based upon papers. But when you're doing your research, you need to summarize everything you did. You don't say the purpose of this research was to do that, but what you do is you write it up in such a way as that the reader can tell right away what the purpose was, what the results were, and what the conclusions were. Succinct means short. By the way, for those of you that said it's got to be a certain length, again, if you read a lot of websites, they'll say that the abstract should be no more than 3 paragraphs long. That's crap. It all depends on what the research is. If you write your thesis, for example, which might have 400 pages in it, a 1-paragraph summary of 400 pages isn't going to do it. It's proportional to the content of what the paper's all about. The introduction. Many of you said the introduction provides background information for your study. That is true unless you have got a separate background section of your paper. Now, you're not going to have to do a separate background section for this grain size project. You are for Moscow Landing. So for this project, the introduction should indeed provide some sort of background information. Now, background information doesn't necessarily mean you go out and start doing a lot of research. But suppose you did a study, or your grain size project was to look at how currents influence the distribution of sediment. One of the first things you might want to say, your first introductory sentence might be, currents are responsible for distributing sediment. They will be related to the grain size that is being produced. And you can quote somebody from doing that if you find it. That is an introductory statement that gives you background about what your project's ultimately going to do. But the most important thing that the introduction does, and this is absolutely vital, it states explicitly the purpose of your research. Now, when I say research, of course, this is a research paper, so if you sample things, if you did a core to determine whether flood events are evident by the sediment being left behind, then somewhere along there you should say, this study examined the potential for flooding by extracting a core from Municipal Park Lake. If you were doing it as a research paper, the purpose of this study is to examine the literature to determine if phosphorite is something that's going to you can find a particular rock. You need to state what it is the research is all about. What do the conclusions do? The conclusions more or less summarizes the results of the paper and gives directions for where you should go in the future. That's the future work component. You guys should all, in your conclusion section, state, in future, I would have done the following, although not that cut and dry. Because if all goes as planned, you're going to be left with more questions than you're trying to answer. All right? So use that as an opportunity to say, in future, someone doing this might want to do the following along those lines. One other thing too, and if you're trying to figure out what all this tense stuff means, there's a difference between each of these as well, each of those three sections. The abstract, because it talks about the contents of the paper, is always written in past tense. This study examined the following. The results were past tense. The introduction, unless you're talking about background material, is talking about future work. Hence, you would use it in future tense. This study will examine the following. And the conclusions, because you're summarizing what you've already done, should normally be in past tense unless you're talking about future work, in which case it's future tense. Okay? All of these aspects of a scientific paper are things that you should preserve when you're dealing with a geology or a research or a science paper. I'm not arguing that if you take an art course, an art history class, they're going to tell you to do differently. But you have to remember, you have to be able to be flexible, writing for the style that is required. Now, one other thing too about the cover letter. In future, a couple people didn't give me the cover letter, the letterhead stuff. What happened? It was online. It's online, yeah. So just there's a blank page. It's in Word. So in future, use that. Okay. Yeah, it's on the web page. It's under the supporting information that's out there. Okay. Be careful with your spelling. I caught several people who spelled Brockhaus name wrong. Don't do that. No, that's intentionally. The word is so out of there. I did intentionally. So you can't spell check it. It's going to come up as a spelling mistake on that, but you always check, especially when you've just been hired on. Make sure you spell your boss's name correctly. And also, it's not Mr., it's Doctor. I don't really care if you call me Doctor or Mr. or whatever. I really don't. But I got to tell you, you get into business, there are some people who wear that like a crown. And if you call them the wrong thing, that means when it comes time to get your pay raise, you might find that you're not getting as much as possible. Make sure you sign your letter. A couple people did not sign their letter. And most of you did this, and I applaud you for this. When you sign your letter, make sure you put your name, print it below your signature line with what your title is. You guys are all geologists in training. Yeah.
You're only supposed to sign that first page.
Yes.
You don't need to do...
Yeah, see, the idea of a cover letter is you say, here's what I did. So you don't have to put additional stuff like the title of it on there. I mean, you can put the title on if you want to, but you don't have to have a header. In fact, I got a couple of people to not do this in the future. And by the way, if those of you that wrote this up as a school assignment, saying like students do the following, or this is what we do in school, remember, you're not really in school anymore. I mean, you are, but you aren't. You're working for the GSSA, so act as if you were actually employed by this company, okay? Look over your comments that are there. If you cannot read what I said, please come and see me and I'll translate it for you as best I can. My handwriting is pretty bad for me too, okay? Now we have one more writing assignment that is going to be due on Thursday, and this one's going to be a little bit more cumbersome, so we have to talk a little bit more about this in a few minutes. This one's redoable. Whether you redo it or not is entirely up to you. Both the cover letter and the assignment are redoable. In other words, if I ever give you something with 2 grades on it, both of those are redoable as long as it's a W assignment, like a writing assignment, and as long as I do not specifically say it's not redoable. Some of the assignments we're doing later on will not be redoable, okay? If you want to redo it, modify the letter and/or the assignment per my recommendations, but I need to see the original. So to get credit for a redoable, you have to give me the new one and the old one as well. You might find it convenient just to staple them together because I have to see what the comments were initially. I'm not going to remember what the comments were, okay? Remember the policy. I will give you up to 10% additional credit if you redo something and address all of my comments. That's up to. It doesn't necessarily mean you're going to get a full 10% because I'll always find other mistakes. Unless it's a simple thing. And for those of you that are looking at your cover letter and saying like, damn, I just didn't sign it and he docked me 2 points. Well, you sign it, you get 10% added to it, you still get your A. You don't have to redo these, okay? So look at what the grade you got. If you got 9 out of 10 on both things, you can redo it if you want. If you're a perfectionist, you can redo it if you want. Doesn't necessarily mean I'm going to take you up to 10. In fact, I probably won't. I'm not going to give you perfect if it's gone through a redoable cycle. If it's worth your time to sit down and make a couple corrections to get a little bit higher, go for it. But if you've got an A already, then maybe you might want to just say, I don't have to worry about it. Okay, so it's entirely up to you. Now, right now, as I understand it, actually, no, I was wrong. You guys got a bitch of an assignment in structural geology, right?
Yeah.
Well, I don't know how you did, but if you're still working on it, when's it due?
Thursday.
Yeah, you know, if it's due Thursday and you're still working on it, maybe not so much of an issue this time around. But, you know, if you have a little bit of extra time, you know, take care of it. All right? Comments, questions, complaints? Complaints can come later. Come see if there's a problem.
Do we need to be turned in Thursday?
It's got to be turned in by Thursday. All right? Now, remember, use the due date calendar, which is up there. But remember, you also have your second writing assignment due, which is going to be significantly less work for everybody, especially because they're in groups. And this is a peer review assignment, which means there's an additional complication along the way, too. And I'll talk about that once we get through today's lecture.